last time I defined what is micro support in mixed characteristic case. So so let me recall the definition. So x over s regular of finite type. So S was S is a spec of discrete variation in mixed characteristic, and the residual field is perfect. And the regular finite type, and we have a sheaf, and closed conical subset as usual. Then we say F is micro supported on C if so there are two conditions. So first the support of F is the subset of base of C and the next condition is that the usual format. So yes, support of F is a subset of
F restricted to excess.
Yeah. Okay, and okay, and HBがseparated of finite type, and W is also regular. So then if H is C transversal, then H is F transversal on a neighborhood of the closed fiber. Okay, so so as Hiroki remarked that so this so they are living only on the cotangent, only on the character P fiber. So this we require this transversality only on the neighborhood of character P fiber.
So on the general fiber, you have the characteristic 0
character 0.
And do you think there should be some relation between the characteristic variety on the general fiber and the one in the characteristic P fiber?
Yeah, so you have the
of course, you're embedding something smooth at the state to have a global coordinates. So I don't know, you have, but it should be intrinsic in some sense.
Yeah, so you have a characteristic cycle on the genic fiber. So if you take the reduction in some sense to the character P fiber, then it should be subset of the singular support in the character P fiber.
Okay.
Yeah. Okay, so example. (4.3) So with this definition, so every sheaf on X is micro supported on the whole Frobenius Witt cotangent band. Because in this case, the C transversality implies the smoothness on the neighborhood of the closed fiber. So, and the smooth motion is transversal with respect to any sheaf. So we have this property. And next property is
injectivity on the FW differentials just implies.
Yeah. It's equivalent. Yeah. Yeah, injectivity of Frobenius pullback of Frobenius Witt cotangent band is equivalent to the smoothness on the neighborhood of character P fiber. So so we have this motion.
Yes.
The injectivity of this map is equivalent to that H is smooth
Okay.
on the neighborhood of closed fiber. Okay, so next one is locally constant. So sheaf, so F is micro supported on the zero section. So this is zero section. If and only if F is locally constant on the neighborhood of characters P fiber. And this implication is easy because if your sheaf is locally constant, every motion is F transversal. So this implication is easy. This implication is the other one is more requires argument, but it's also true. I will skip this. This is easy. Okay, so we have a good definition, but as I said in the beginning of the course, the theory is far from complete. So let me give a list of open problems.
Sorry, example 2.
Yes.
It's the less easy direction is even in geometric setting, it's not so. Even in the characteristic P geometric setting, this less easy direction is not true.
This implication in geometric case? Yeah, in that case, we can use, in this case, it involves acyclicity. So it just says the sheaf is locally constant.
You have to go through the local.
Yeah.
So I think some time ago you had a weaker form of the existence of the micro support.
It will come.
It will come. Maybe you will discuss it. Okay, so I don't want
The
to.
saturation, it will come later.
Yeah. Yes, yeah. It will come. Yeah, saturation will come later. Yeah, before saturation, I need to introduce a relative version. So the first one is the existence of single support. So I just wrote down the definition of micro support, but as usual, the single support is defined as the smallest one on which F is micro supported. So existence, so we don't know. So we want to adapt the method of Beilinson, but the Beilinson method required two modes, H and F, so Q and Q check. But here we have only H. So
of course it should come as the extra facts like that it commutes with localization and so I mean the other thing that we proved together with the existence, like compatibility with the risky localization, should also be part of the.
Yeah. Yes. So reduction to project space goes similarly, but so yeah.
Okay, so some of this can go on, but not can go through, but not.
Yeah, reduction to Pn is okay. But so for Pn you want to work with Radon transform, but so with Radon transform we play with Q and Q check, but here we have only one Mossum. So we needed to, so
So maybe it is still, but still you have more coordinates. So maybe it is like a partial Radon transform in some.
Yeah. So this way we get only partial one. So yeah, to work with this one, so I will introduce the relative version. So I'm going to introduce a relative version with H and F. Then still I can't prove the single support of this relative version, but if we further introduce a saturated relative version, then we can prove the existence. So I will explain more detail later. And next one. So suppose we have the existence. Then next question will be the dimension. So in the geometric case, so Beilinson proves that every irreducible component has the same dimension as a variety itself. So, but we cannot expect this in mixed characteristic situation because this is similar, analogous to the situation where we have map to curve. Okay, and they take close point. Then our singular support will be just the recession to the closed fiber. So this irreducible component may have a dimension n or n minus 1. So n is dimension. So we like to have two types of component. But so Beilinson proved this property. So it's natural to try to transplant his method, but I don't know how to do this.
So which result, which estimate do you have on the dimensions?
I don't have an estimate even. I don't have any estimate even.
Even high, lower or high or?
Yeah. I cannot say anything. Yeah. Okay, so this. And this is a basic question, and I can go further. So next question is description at codimension 1. Generic point. So suppose D is regular divisor. Generic point.
But this means the generic point of the special fiber.
Yeah. Generic point of a divisor. Yeah, divisor is in the character P fiber.
Okay. But the X is the one six.
Yeah. So U is the complement, and J is open immersion, and let's say F is the zero extension, and this G is locally constant. So let's consider this case. And regular irreducible divisor. And Guzai be the generic point. And in character P, the residual field is character P. So K will be the fraction field of OX. So we have this DVR and completion. So we have local field and the residual field, the residual field is some function field in character P. Then this G defines representation of GK, absolute color group. So we want to have this description of the singular support. So it's fiber at this point in terms of this Galois representation. So let me recall what we know in geometric case. So here X is smooth over some field K, character P. And we consider a similar situation.
But here, since
Yes. Yeah, so we are interested in the mixed characteristic case, but let me begin with reviewing geometric case. Okay, then we also have Galois representation similarly. Then we have upper number filtration. Defined by Abbes and myself. So using this filtration, we have slope decomposition. And V1 is just the tame part. So P is a wild inertia. One plus wild inertia. So we have such a decomposition. So for simplicity, let me assume V is VR. So we have only one component, and we are in the wild case. Then this defines so we have further decomposition by characters. Because in this case, we know that this graded quotient. So this is abelian and killed by P. So we have such a decomposition by characters. And further, we can identify the character group so we regard this as a F vector space. Then we have injection F is the residue field. F bar and K bar is a separable closure. Omega 1 F sorry, omega 1. So we have injection.
So you take the differentials.
Differentials.
Tensor over.
Tensor algebraic closure of the residue field.
Tensor over the.
Over it. Yeah. Yeah, so we have such injection to the
So
to
K bar is the maximal ideal of the
yeah
normalization in the center of explosion.
yeah. So MK bar R is
So the valuation is at least
variation is
the normalized valuation.
you have
Okay. It's in terms of the valuation, of course, not in terms of power.
yeah. So this is one dimensional. So we have a vector space of dimension 1. So the target here is the geometric fiber of the cotangent band, and we have map from line to this cotangent, the fiber of the
And
cotangent.
this map is given by the map is what?
The refined one.
Yeah, this is analogically defined one. So each time, so if we have character, then we have corresponding motion here, and this is injection. So if you have non-trivial character, then you have injection from this line to this fiber of the cotangent band. So in the geometric case, the singular support of this zero extension, and if you take geometric fiber at above this JF point, then this is union appearing in this character decomposition of image of this character form. So this is rank 1 vector space so in the fiber of this cotangent band. Okay. Yeah. So in geometric case, we have such description of singular support in terms of ramification theory. So we want to have something analogous, some analog for in mixed characterized case. So in mixed characterized case, so yeah, So we have similar decomposition similarly, and if we make this simplifying assumption, we get this decomposition by characters. And here, so and we have similar injection. The only difference is here. So in mixed characteristic case, we replace this fiber by this Frobenius Witt yeah, we just need to put f, maybe I didn't like 1. So we just replace usual differential form by Frobenius Witt differentials. So we have such injection in mixed characteristic case, and we expect to have similar description.
Even in mixed characteristic case, this injection is constructive.
Yeah, it's defined, yes. Okay, so this is the arc expectation.
So you expect it to be of codimension 1. So it's
Yeah, it's a description in codimension 1, yes.
no, but the dimension of this cycle you get.
Yeah, so it's it's in dimension n case. So it's
So the codimension 1, it's dimension n.
yeah, because our device is totally included in the character P fiber. Okay, the last thing is CC. So if single support is if we write single support as a union of irreducible component, then CC should be. Sorry?
Problem 4. You are now.
Yeah.
This was a problem to prove this in mixed
Yes.
characteristical.
Yeah. Yes. Yeah.
Okay. And in the 10 case, you have just the zero section, or what do you have in the 10 case?
10 case, we just have conormal bundle. Conormal bundle.
To the to the divisor.
Yeah, conormal bundle with this divisor.
Okay.
Yeah.
And this can be proved, I think. The 10 case.
10 case must, yeah, 10 case can be proved, yes. Okay, CC. So CC should be something like this, but it's not convenient to have two type of component. So I don't like to have this dimension n-1 component. And there is a, so to get rid of them, so I assume, so we consider virtually, namely we consider K group of some in this group, then and assume that the rank function, so this is the rank function. Let's do to the J fiber. So the rank function is the constant. So I assume this simplifying assumption. Then we expect that here we have only those components such that the dimension is the same as under this assumption, I expect to have that only dimension n component appears in this sum. Yes? Yeah, the rank function on the generic fiber is a constant zero function. So virtually there's nothing on the generic fiber.
But couldn't you always take a direct sum of something with its shift by 1 and always have rank 0?
Yeah.
But then the singular support would not change?
So singular support, there is singular support, but this character cycle is...
I can cancel some components of the singular support.
Yeah.
Thank you, yes, okay.
Okay, so if the rank function is 0
they're on the generic fiber.
on the generic, so this means that the class in the Grothendieck group on the generic fiber is
So there should be no...
okay, but since the generic fiber is in characteristic 0, it should be that knowing the rank function determines the singular.
So in the generic fiber character 0, so there's no wide ramification. So this rank condition should be enough.
Okay, so there is no contribution from the generic fiber, and therefore it should be just.
Okay, so let's assume this. Then we can expect, and suppose that they are defined, then we expect to have compatibility with with pullback by properly transversal. So transversality we are already discussing, and this property means that the dimension is fine. So namely, so under this condition, so we have before pullback we have dimension good dimension. But we need to work with this pullback, and in general we have only estimated from below. But the property, this means that we want to have equality here.
For all irreducible components, okay. Well, instead of n, you should have the dimension of the source. Instead of n, in H0C.
Sorry. Yeah. So this is dimension of x, and this is dimension of w. Yeah, thank you. So we can also expect to have compatibility with push forward by proper motion. And in the base case, if x is the base spec of OK, so in this case, this CC should be the rank of the closure fiber, minus 1 conductor of the generic fiber times. So this is just 1 point. So if we combine this push forward property and this normalization, then they should imply a conductor formula.
Sorry, if rank is 1 and swan conductor is 1, this is gonna be 0. So even in the wild case, CC can be 0 for when, for example, rank is 1, swan conductor is 1.
So in this, so this is close.
This is not 1 point, this is 1 line. Ft star S is a one-dimensional vector space.
This is a close point and this is a generic point. So but I'm making this this condition. So I think it looks a bit strange, but on the generic fiber, I assume the generic rank is 0. So it should be okay.
See, this is when F has generic rank 0?
Generic rank 0, yes. I need.
This is a continuation of.
I keep assuming this condition. So this the combination of that compatibility and this normalization should give a conductor formula, and a special case where a dimension x is 2 and f is if we consider the difference of rank 1 sheaf with constant sheaf, so in this case, a student of mine, OA, he defined a candidate of CC and proved conductor formula.
There's some cleanliness. So we are in dimension 2. So.
Dimension 2, so you don't need it. Okay, so there are open problems. Okay, now, so I said that I need to introduce a real version, so let me continue. So real version. So x as before, so x regular.
This conductor formula doesn't include the Bloch's conductor formula?
No, because we have this quotient sheaf.
This?
The question was that if this include block the conductor formula, but the block the conductor formula is the case for constant coefficient, and yeah, and yeah, I always assume this condition. Yeah, difference. Yeah. It's always like this. Yeah. Okay, so X regular over finite type over our S. And F sheaf on X and C closed conical subset. Yeah, as before. Okay, now we say our sheaf F is S micro-supported. So this is so I'm going to introduce a relative variant with respect to this base S. If the following conditions are satisfied. So this is along the usual format. So I would just like.
You mean C micro-supported or S?
Sorry, S micro-supported on C. Yes. Yeah. Thank you. Yeah, so I will like a statement, but there are some terminology which is not yet defined. So first let me write it down, and then I will define more, continue to define them later. Okay, so let H. So this time we have two morphisms. Separated morphisms of regular schemes of finite type over S. And further assume. So I don't assume regular smoothness of W, but I assume smoothness of Y. Then if this pair is C acyclic over S, so I haven't defined this, so I have to explain what this means. Then HF is F acyclic over S. So this I haven't defined either, so I have to also define this. So in the geometric case, we didn't have this over S. On the neighborhood. So we always have this restriction because so we are working with Frobenius Witt cotangent band, which is defined only on the character P fiber. So we always need to restrict make this restriction.
So does this have an analog in the geometric case where S is, let us say, some smooth variety, and you are interested in some closed point, let us say, and then can you make those notions and this?
Yeah. So if S is a spec of perfect field, then we go back to the Beilinson definition.
And can you have like S be a curve over a perfect field? Instead of a mixed characteristic, it should also work with equal characteristic. Let's say S.
It's not exactly because I need to, It's a little modification. Yeah, it's not exactly equivalent. Okay, so I needed to define this notion. And to justify this definition, let me tell you about some heuristic observation. So we are in the mixed characterized case, so we don't have base field. So, but let's pretend that we have a base field. S has base field K that can be F1 if you like. Yeah, and we suppose we have motion to a smooth scheme. Over K. Then, so we consider this pair, and this will be F acyclic if so we have this product motion is F G0 transversal for any G0 on Y0. So we had this interpretation last time. Okay, so but this fiber product, this you can like this if y is base change to S. So this y0 is some hypothetical thing, but once you take this fiber product, you go back to the real world. So, but still, you have this hypothetical one. But if you take G to be the pullback of G0 to Y, then this also you can write the transversality like this. So here G is sheaf on Y, so it's not a hypothetical one. But here we have this condition. So this means that if one can determine which G comes from Y0, then we can make good definition. So we require this transversality only for such G coming from Y0, then we can make a definition like this. So to determine which g comes from y0, if g comes from y0, then its micro support should also come from y0. So here our y is smooth over S. So we have injection like this. And we consider closed conical subset on which G is micro-supported. And so this y0 is a virtual object. So if y0, if we have y0, then this bundle should be product of this and product of that. But we don't have such product decomposition. But we still want to say which C prime come from y0. So that means that this C prime should be perpendicular from this pullback. So I define so we say so this is similar to definition we have seen last week. So this y to s is C prime acyclic if the inverse image if the inverse image of C prime is a subset of inverse image of C prime in this pullback is a subset of the zero section. So we don't have direct sum decomposition, but so we have this injection, so we can consider the pullback here, and we require this condition. The inverse image is a subset of the zero section. So now I can make a definition. So first part is, so let y smooth over S and G a sheaf on y, then we say G is S acyclic. If so, by this I mean that it coming from some y0. If there exists C prime like this, on which G is micro-supported, and such that y is C prime acyclic. Yeah, I want to define the condition that G is coming from y0 in terms of micro support. So this G is micro supported on C prime, and I require that this condition on C prime. So using this, using this, I define this condition. So we have, so that H and FB as in 2.4. And also I also need F and C. Okay. Then we say H and F is S. Sorry, F acyclic over S. If for every G like this, G on Y, which is S acyclic, this product monstrum transversal. So this is just this heuristic observation where this condition on G is formulated like this.
So is this condition is implies the S acyclic, it implies that R phi is 0?
Implies what?
That R phi, that the vanishing cycles of G are 0. Does it?
So this is something weaker than the local acyclicity. Yeah, because I have this restriction on G, so
the condition that G is S acyclic, where G is a sheaf on Y which is smooth over S. Does this? It is clear. Is it clear from the definition that it implies that
here.
Yes.
This I'm not so sure. So I have to think. Yeah, I cannot answer immediately.
Yeah, because well, you have to unwind what you have done. So because
Yeah. It's a natural question, but I don't have the answer immediately. Thank you. Okay, so this is the definition for F, and I also need to define for C. But maybe yeah. Let's take a 5-minute break and continue after. Yes. Yeah. This in fact implies this is G acyclic. Yeah. One can prove this using that relation between the transversality and acyclicity. Okay, so now let me define this one. Yeah. So X say as in 4.4. So first H. So I introduce that terminology. So this is also as in 4.4. Then we say this pair is C acyclic over S. This condition is rather complicated. So we consider pullback times pullback of the everything, and its intersection with the kernel. So up to here, it's similar to the definition of acyclicity. So on this side, we just take pullback, and on the second factor, I take the whole thing here, and I consider the intersection with the kernel. So this, and in the geometric case, we just require that this intersection is the kernel of the section. But here, I require this to be a subset of the kernel. So I'm just copying the same thing here. But this goes to the pullback of the fiber product, and I require this inclusion. So the idea is somehow similar to this F definition for F, but it's less straightforward, so it's not easy to explain. But one point is that if W is smooth over this fiber product, then this condition is trivially satisfied.
Okay, so this is one dimension. So when y, you assume y is smooth over.
Yeah, y is smooth over S.
So this kernel is one-dimensional sub-bundle, yes?
Yeah, yes.
Okay.
Yeah. And we say this C is S saturated if it is stable under the action of the pullback of this. So this C is closed conical subset of the Frobenius Witt cotangent band. So we have natural map from here to there, and this saturatedness condition is that it is stable under the action of this line bundle. So let me tell you two examples. The first is, so suppose HF is C acyclic and Y2S is C prime acyclic. Then we have this product motion. So this is the sum of the two pullbacks transversal. And second property is, so assume H is C transversal, and at the second motion, I just take structural motion to S. Then if this C is S saturated, C is S saturated, then this pair is C acyclic over S. So once you get to this definition, this is rather elementary. So I will just skip this. And using these properties, I can give you the relation between abstract one and relative one. But to prove the relation, I need one property which I don't know how to prove. So suppose we have two sheaves on X and assume F is micro-supported on C and G is micro-supported on C prime. And for the so if the support of the intersection is empty, so if they are micro-supported on a different direction, then the tensor product is micro-supported on the sum.
The sum, this means the sum of vectors taking the closure, okay.
Yeah.
And when you take the sum up there, do you take the closure also?
In this case, by this assumption, they are in the different direction. So I think it's I don't need to take closure.
Okay.
But by the way, this is some transversal over S, right?
No, transversality there is no S. Acyclicity you have relative. For the acyclicity you need a base, but the transversality there is no base. So more weakly, yeah. So this is the case where we have only one scheme, but now we have F on X and G on Y, and Y is smooth over S, and yeah, again F is micro-supported on C, and G is micro-supported on C prime. Then this external product is micro-supported on the sum So this is a special case of that one.
So you have the expectation in the geometric case?
Yeah. In geometric case, this is proved. Yes. Yeah. So to statement. So assume F is micro-supported on C. So this is an abstract one. And if this expression holds, then F is S micro-supported on C. And the second one, so suppose F is S micro-supported on C, and then if C is S saturated, then F is micro-supported on C. So the first statement says that the absolute one implies the relative one, but I need to assume this property. And the second one says that the relative one implies absolute one, but I need this condition, saturated.
Why you don't need the closure in more weakly? Why you don't need to take the closure of the sum?
Sorry. Yeah, I need to, because I forgot to say one thing. So this C prime should be S acyclic. Yeah, thank you.
Okay, so this means that it is not, it is small. Okay.
Yeah. Thank you. Okay, so let's prove this. So we want to, so we assume F is micro-supported on C, and we want to show that F is S micro-supported on C. So,
Did you define saturated or did you?
Yeah.
Okay.
Stable by the action of the line. Saturated with
yeah.
Okay, it's stable under the action.
Okay. Yeah. So the conclusion is it's S micro-supported on C. So we need to test by H and F, which is C acyclic over S. And so assume. And we want to show that HF is F acyclic over S. Okay, so we take G on Y, which is S acyclic. And then this acyclicity means that this motion so we want to show that this is this transversal. But this sheaf is by expectation, so this is micro-supported on this this sum. And yeah, by this property, if this pair is this.
C is micro-supported where? C the same C or?
Sorry, this is C prime, and so S acyclic means that this is micro-supported on C prime, which is S acyclic. Which is such that Y to S is C prime acyclic. Yeah, thank you. So G is S acyclic. That means G is micro-supported on C, this on such C prime. And by that example, this motion is this transversal. And by expectation, this external product is micro-supported on this sum.
So you have to go from tensor product to external product.
This is external, yeah.
And the the assumption is about the tensor product.
Yeah, yeah. So this more weakly.
So on the more weakly expectation.
Yeah.
No, okay, but the more weakly is including this assumption on cyclicity of product.
He's using just the more weakly.
Only the more weakly.
Yeah.
But the more weakly comes from the tensor, doing the tensor product on.
Yeah. Yeah, if you apply this to the pullback, then we get this property.
Okay, so you have to know compatibility. Okay, but you have this in your theory. Okay.
Yeah. Okay, so using that expectation and that property, we have this first one. And second one, so assume so now we want to prove absolute one, so we just take one more sum and assume transversality, then we want to this H is F transversal. Okay. So in this case, we take F to be the structure moves to S. Then by this and the assumption that so we assume that S is C is S saturated. Then HF is this pair is C acyclic over S. So this yeah, then so we can take as G, we can just take constant sheaf. Then this implies that this H and F, so this map is this transversal. And this is what we want. Okay, so we have this implication. So we don't know the existence of a single support, but if they exist, this lemma implies that if SS exists, and also relative version. So I didn't define relative version, but we defined the micro support, relative micro support. So we can, as usual, we can define relative single support as the smallest one, and relative saturated single support as the smallest saturated one, on which F is micro supported on S micro supported on C. So SS and if they exist, this lemma says that we have this inclusion. So this means that relative. So this is the correct one. So the relative one can be too small, and the saturated one can be too big, but the difference is just one dimension, because saturation means that it's closed under the line action of line bundle. And moreover, if this motion is 0, then the condition is trivial, so everything will be saturated. So if X is far from smooth over S, then these two should coincide, and these all three must be equal. Now I can state a theorem. So I can't say anything about these two, but the last one, so to prove this, I can, so the proof is same as Beilinson. So I can reduce to the case to projective space over S. And if your X is smooth, and if we consider only saturated one, then so instead of working this cotangent bundle, Frobenius Witt cotangent bundle, we can also work with the Frobenius pullback of cotangent bundle restricted to characteristic P fiber. So because if X is smooth over S, then we have this exact sequence. And if we assume this saturatedness condition, so that means it's stable under the action here. So the saturated closed conical to consider saturated closed conical subset here means that you just consider closed conical subset here. And this Frobenius is homeomorphism, so you can ignore this. Then, then you can literally copy the argument of Beilinson to prove the existence. Okay. So in the remaining time.
So but you still have expectation 4.8. So because you don't prove completely expectation 4.8, do you know that there is a smallest saturated conical subset so that F is micro-supported? You do it with S micro-supported, and in the lemma you need expectation 4.8. So this means that to prove that there is a smallest saturated conical subset on which F is micro-supported, you need some expectation 4.8, or not?
In the theorem, you don't use the expectation.
In the theorem, I only work with saturated ones. So this theorem is independent of this lemma. So I don't.
Yes, okay.
So this is only the existence of this. So I can't say anything about the existence of these two.
So you don't say that there is a smallest saturated conical object on which F is micro-supported without S, just because of this expectation. So you don't say this.
Yeah. Okay, so remaining time, let me try to prove this proposition. Thank you. So this is essentially Braverman. Gaitsgory. Okay, let me recall the statement. So F is most of finite type. Over excellent regular Italian scheme. Okay, and F is sheaf on X, and assume X to S is F acyclic, universally F acyclic, and Y is smooth. Then the following are equivalent. So the first one is this F is F acyclic, and the second one is for any sheaf on Y, this graph motion is transversal. Okay. Okay, let me try to prove this. So in second condition, we may consider only G to be I star of L, where I is immersion and L is locally constant. So by some research, we need only consider these G. And further, this V is regular. Okay, now we consider a Cartesian diagram. X cross Sy. So W is X cross x of yv. So this is our most gamma, and let's call this gamma prime, and they are just projections. Okay. Then I already let me also recall another proposition. This this is you can find in SJ 4.5 or book of Fure. F of finite type and F sheaf on. Maybe I don't need a finite type. Then the following are equivalent. F is F acyclic. So for in every Cartesian diagram, such that I is imagine, and for any G on V, this conical motion H star F, then is star large G is our isomerism.
That's twice H upper star. Does it look?
Sorry?
You wrote twice H upper star.
Yeah. Sorry. Yes. Yeah, thank you. Okay, so we have this proposition. And here also, this G, so we can also assume here G can be locally constant. And this condition so with notation here, so we can write this as gamma star of F external product of I star of L. So I replace this G by L. And this one, similarly, so H star of gamma prime star of F external L. So the second condition is that this is an isomerism. Okay. So we want to prove that these two are equivalent. But now using that interpretation, I can reformulate it as follows. the first one is acyclicity, so it rephrase like this. So for every immersion and L on V locally constant, the most there, so this gamma star, gamma star going to H star gamma prime star this is our solution. So this is the interpretation of the first one. And for the second one, so similarly, and the immersion of regular scheme. For the second one, it's also the same thing. So immersion and locally constant C from V. Then the transversality, let me just write down the transversality. So gamma star of F tensor gamma sheaf of lambda is gamma sheaf of this one. This is isomerism. So we want to prove the equivalence of these two. Okay, so and this is the kind of C. Now I write a commutative diagram. So the upper line is just this one. Okay. And here we have this one. So I'm going to this one, but with tensor with pullback of that one, and take direct image. So this is almost a twist of this. And then from here to there, and if you go from here to gamma prime sheaf of lambda, then we have C for gamma prime. So we can go to go there. So this is almost H star of C for gamma prime. So this is C for gamma. And here is base change isomorphism. So we have this is. So this is isomorphism by proper base change. And we need to check, of course, check the commutativity, but I skip this. So we have this isomorphism. Okay, so we want to show that isomorphism here is equivalent to isomorphism there, and second map is here, and the vertical map here is almost the same. So this is isomorphism is equivalent to, so by this regularity. This immersion is regular immersion. So so this is locally constant. So we can ignore this part and this is isomorphism if and only if that is isomorphism. Yeah. So if this was isomorphism, then they clearly we get the equivalence. But we don't know this, so we have to work a little bit more. So I have to give name.
So start of sigma 1.
Sorry?
It's almost start of sigma 1. This is what you.
Yeah. I always put this star somewhere wrong. Yes. Okay. Okay, so let me call. So in my note, this diagram is 3.4, and this motion is 3.3, and this is 3.2, and this 3.5 is this motion before taking H star. So H is gamma prime star F tensile 10 star H star gamma shriek lambda going to okay. And let me call this A. Okay, so the claim is the following are equivalent. The first one is that 3.5 and that A are isomorphism. Second one is 3.3 is isomorphism. And the last one is all arrows in 3.4 isomorphism. So we claim this. Okay. Let's prove this. So 3.5 is isomorphism. So because we assume this as isomorphism before taking H star, so after taking H star, so of course we have isomorphism here. Okay. And we also assume that this A is isomorphism. So yeah, and the diagram is commutative. So this implies 3. Okay. And second implies the first. So 3.3 is isomorphism. So we assume this is isomorphism. And we know that that is isomorphism. So that means this composition is isomorphism. Okay. But this H is the base change of I. So if I, so our I is immersion, so H is also immersion. So if this is the isomorphism, then by taking the adjoint, I can move this H star, H lower star as H upper star here, and still we get isomorphism. So I said H upper star of this is isomorphic to that one. And this exactly means 3.5 is isomorphism. So let me write. So second, by assumption, this composition is isomorphism. And by adjunction, 3.5 is isomorphism. So 3.5 is isomorphism, then this is isomorphism. And by our assumption, that and that, they are isomorphism. So, yeah, so A is also isomorphism. And yeah, then 1, 2, 1, 1, 3, 3, 2. Yeah, so we need to have this, show this, but this is obvious. Okay, now, so they are equivalent. So, we have this 2 implies 1. So 2 implies 1 means so 2 says that 3.3 is isomorphism. Then this A is isomorphism, and A is isomorphism means this is isomorphism. So this always already shows that 2 prime implies 1 prime. Okay, so we want to our remaining task is to show this implication. Okay, so assume 1 prime. And we want to show that 3.3 is isomorphism. Yeah, 3.3 is isomorphism. But so assuming one, so this means that A is isomorphism. And we already have this equivalence. So to prove 3.3, so this is it's enough to show that enough to show 3.3 is enough to show 3.5. Okay. So first we consider the case where I is open immersion and L is constant sheaf. So in this case, yeah, so in this case, so why is this? So by our assumption, so why is it smooth? So this base change is smooth. So this gamma is a section of smooth motion. So and our sheaf here is F is here, and we just take pullback of F. So by the transitivity of transversality, this gamma of transversality gamma is transversal. Here, so this smooth motion is F transversal because of Poincare duality. So gamma is a transversal means that this upper line, this 3.3 is isomorphism.
You don't go through 3.5. You go directly to 3.2. You don't go through 3.5. You go directly to 3.
Yeah. Here it's okay, but the next one. Oh, sorry. The next one is I is closed immersion. And I is what? Sorry, L is so yeah. So this is argument. So I already out of time. So I just say that I use distinguished angle. So yeah, so we have a closed immersion, so complement is open, so we can use the first one. The last one, so in general, yeah, so in general, so we want to show that yeah, so this is isomorphism. But this L is locally free. Sorry, locally constant. So that means that it's enough to prove this isomorphism for a single non-trivial locally constant sheaf. Yeah, and I is general, but so that so we can argue locally. So we may assume I is closed immersion, and so as I said, L can be any non-trivial locally constant sheaf. So, but this case is already proved, and this is a non-trivial locally constant sheaf, so it's done. Okay, thank you.
This you said that this is in one of your papers. This proof is in one of your papers.
Ah, yeah, yes.
Okay.
Yeah, the most recent one.
The one on the okay.
Yeah.
So, excuse me. So in this I being open immersion and L being the constant case, the above. So you improving 2 prime implies 1 prime. You show first you assume I is an open immersion and L is the constant sheaf. And what?
Yeah.
Yes. And you get 3.3 by the transitivity condition.
Or 2 prime implies 1 prime or 1 prime implies 2 prime? What are you?
Sorry, 1 prime implies.
Okay.
Yes. And you used transitivity.
Yeah.
And what is the argument? So you said.
So I want to show that this is the transversal.
Yes.
And well, we know this is the transversal because it's smooth.
But the sheaf is the F tensor I or star of lambda.
Yeah, sheaf is this, so it's just pullback of F.
But use I is an open margin, right? So L is living on V, the open of Y, and you push it forward to Y.
This is the first case. We started by the first case, open immersion, and he said that we can assume L equal lambda. This is the first case.
L is living on V, right?
Yeah, V, but I is open margin, so yeah, maybe I was confused with V and Y. Yeah.
But you consider star push forward, right?
Huh?
You consider star push forward.
Push forward. This is yeah. Here it's everything is over V. So you.
You're proving 3.5.
Yeah.
Do you?
So first, let's take the technical question. Any questions?
And as usual, there will be notes on the web.
Yes. The full notes will be already on the full notes.
Yeah. I will put this. Yeah.
Okay.
Other questions?
Is it sometimes useful to interpret acyclicity as something being dualizable?
Sorry.
Sometimes is it useful to interpret acyclicity as a dualizability sometimes, or?
Dualizability. Yeah.
You go from one point to another, but there is also other ones like.
I didn't.
No, I don't know, but just in general, I mean, even in the whole picture, it's sometimes useful to.
Yeah, maybe, but I didn't go into it. Yeah.
So it seems that Wager has also problems to understand the proof. Of Gaitsgory Braverman.
In the QL. The l-adiques, of course, the
So do you understand it in the l-adiques?
No, because several years ago there was some emails with Gaitsgory and there was this.
So what he said?
Can you explain the problem?
But the problem is that all the theory, like of l-adic sheaves, like going to minor balls, and I mean this doesn't work in the l-adiques, in the classical way of doing l-adic sheaves, which requires some. So it's not. So I thought it's nonsense in the l-adic, but I didn't know. Maybe now, of course, there's more mechanisms with very sophisticated things. But I'm not sure if how to.
So
Actually,
the
I don't
conclusion of the
remember.
previous discussion is that it was
No, there was like in 2017, there
Yes.
was some discussion with Gates. This reference was given in
Yes,
some old
yes,
email,
yes.
and I looked at it and I did not. So I had the same impression, maybe roughly like, and now I didn't look at it recently,
Okay.
so I cannot say. And I don't remember now those arguments are kind of translation of what they do into. Is essentially the same as what they but I
But
don't
for
remember.
Yeah, I try to understand what they wrote.
Yeah, and also why excellent. Of course, excellent helps to make things sufficiently regular on some small, but it should not be and regular. Yeah, this I don't.
so why excellent regular?
Yeah, because I want this V to be regular.
And this is useful for.
So by divisions, I want to take some arbitrary sub-schema and take it's open, then I want it to be regular.
Why?
Yeah, because I need to work with this I acyclic.
Okay.
Okay. Other comments? If not, let's take Takeshi again.